Hi, my name's Eric Bauer. I did real-time shadows on complex objects by Gabor Nagy. Shadows are necessary for realistic-looking rendering scenes. This shadow over here on this hairy teapot looks pretty realistic as the light moves around. The hair, not so much. Ray tracing is a technique that is too slow for real time, but it does give you nice realistic looking shadows. For normal rendering in real time, you need special algorithms to generate your shadows. The algorithm I'm going to talk about is pretty simple. It only has to do with point light sources, and point light sources create these sharp shadows where you have no fading between the area in shadow and the area not in shadow. Here are the steps for this algorithm. First, we'll create a shadow map for every light and blocker pair. So if you have two blockers and one light, you'll have two shadow maps. If you have two blockers, two lights, you'll have four shadow maps, and so on. Then you project the shadow maps onto the receiver object, and then you render the receiver objects with the texture applied. Here's a visual representation of the shadow map creation. We're taking a perspective from the point light source at the blocker object and creating the silhouette shape of the object and putting it onto a texture that we can use later to render the shadow on the receiver. The first step will be creating the shadow map. This is the majority of the process. What we do first is define a new coordinate system, the light coordinate system that's origined at the light. We point the z-axis directly at the blocker, and determining that direction, we do something called the mean direction vector, which is drawing pointing a vector from the origin at each vertex of the blocker and averaging those. So we add them up and then we divide by the total, and that gives us a direction that is generally at the center of the blocker. There's an optimization you can do with this equation. You can pull out the p-light term, pre-calculate p-light NV. What we're going to be doing to get z-light is normalizing the mean direction vector. So because of the fact that we're going to be normalizing it, we can remove the division at the top, and that will speed up the calculation a little bit more. Now that we have z, we can calculate x and y of the light coordinate system. It's irrelevant what they are. The z-light is the only one that really matters. The best way to calculate the x and y vectors are to just do a cross product between z-light, which we just calculated, and a unit vector with two zeros and a 1, and the 1 will be the smallest z value to eliminate floating point errors. So a cross product always gives you a perpendicular vector, so that will give us v cross z is x. We can normalize x, and then x cross z is y. So what we need is a transform to transform all the vertices from the blocker coordinates to the light coordinate system. So you can apply just take one transform and apply it to the blocker vertices, and you end up with the same vertices in the light coordinate system. Here we have the world to light transform, and this will convert any point in the world coordinate system to a point in the light coordinate system. So we can we can take the transform from the blocker coordinate system to the world, multiply it by this to get the world to light transform, and that'll give us a blocker local coordinate system to light coordinate system. And once we have that, we want a perspective transform, a projection matrix from the light source at the blocker. And it gets a little convoluted in the mathematics, but here's the projection matrix to view from the light source at the blocker. And what this is doing is trying to get a point of view that just fills the blocker, just fills exactly your perspective. So if you're looking at this blocker, the very edge of the blocker will be at one edge of your view, and the other edge will be at the other edge. Here's a visual representation of that perspective. What you don't want is either this scenario or this scenario. So that perspective projection gives you a perfect view of the object, and then you can apply these transforms. You do the blocker to light transform times the blocker projection transform, and that gives you one final transform that you can all this stuff can be pre-computed, so you can pre-compute this, and then you're just left with this. This is all you really need to store. So now that we're done with creating the shadow map, step 2 is projecting the shadow map onto the receiver. It's the same kind of thing. The paper just gives us this matrix transform. It will take a point on the receiver and give you back a value between 0 and 1 on the x and y of this shadow map that we created. So if you get a value between 0 and 1, you just look up on the texture if it's in shadow, if it's not, if it's in shadow, or if it's not in shadow. If it's less than 0 or if it's greater than 1, then we do something called texture clamping, which means you just repeat the last pixel on here. So everything outside of the shadow map is essentially black, which means it's not in shadow, which means that the edge pixel of your shadow map needs to be black or not in shadow, so that when you repeat it out this way, it's all out of shadow. So the third step is rendering the shadow. To render the shadow, after you've projected the texture, the shadow map texture onto the blocker, you just subtract. You use subtractive pixel blending, which subtracts color intensity at the spot of shadow. So this is a dual pass technique where you first render the texture normally, then you go back, and anywhere that there's shadow you subtract. You're basically subtracting RGB values where the object is in shadow. If you have multiple light sources, you just do another pass. You do a pass for each light, and you subtract intensity further if there's overlapping shadows. So anywhere that's shadowed by it's in shadow of 2 light sources, you'll have it darker than if it's only in shadow from 1 light source. If there's multiple blockers, you actually have to remember, if you have multiple blockers but only 1 light, you have to remember where you've already subtracted, because you don't want to subtract twice for the same light for the same spot. There's no need to recalculate the shadow map if nothing moved, but if either the light or the blocker moves, you have to recalculate the shadow map. This technique produces sharp shadows, so that means it can only be used for point light sources, and it'll look a little unrealistic because of that. You also need to account for shadows on the back of objects. You want to check if the face that you're projecting onto is actually facing away from the light, in that case, it's all in shadow. This paper just mentions that. It doesn't actually tell you how to do that. And one final thing: this is a very simple algorithm, and it's not really used anymore. Not especially not on newer, like high tech games that you see. But it is kind of the basic concept that is used for real-time shadows in newer games. They do use things like shadow maps. These two techniques, shadow volume and shadow depth mapping, are used a lot more now, but they have the same basics as this technique, just a little more in depth, a lot more optimizations. And there's actually a lot of shadow mapping techniques, all with their own little differences. And you can go to this link here to see all of them. There's probably like 30. So there'll be I'll post in the discussion board. You can ask questions and I'll respond. Thank you.